Welcome to the fascinating world of mechanics, a fundamental branch of physics. We can find that every simplest thing in this world needs the study of mechanics to understand how it functions. Exploring the physics behind everyday phenomena, from the smallest moments to the grand celestial motions. The study of mechanics reveals how the slightest change can lead to significant transformations. Get ready to uncover the science that shapes our physical reality. First, we are going to understand what is force. A force is a push or pull upon an object resulting from the object's interaction with another object. Whenever there is an interaction between two objects, there is a force upon each of the objects. When the interaction ceases, the two objects no longer experience the force. Force only exists as a result of an interaction. Force can have two effects on a rigid body, which can cause two types of motion. Translation motion. This motion is characterized by a change in position, displacement, without any change in the object orientation. For example, we can think about a car moving forward. Here, as we can see, that the linear displacement of the car is an example of translation motion. If we observe the clip further, we can see that the wheels are showing rotational motion also. So we will now be trying to understand what is rotational motion. Rotational motion. When the object moves around a central axis or a point, this kind of motion is rotational motion. Examples include a spinning top, a rotating wheel, or the Earth's rotation on its axis. Let's take a moment to appreciate something as simple as opening a door. Ever notice how we instinctively push or pull near the edge, far from the hinge? That's not just random, it's all thanks to torque, the rotational force that makes objects spin around an axis. You can think of a seesaw. If you sit closer to the center, it's harder to lift your friend. But if you slide all the way to the edge, suddenly you are the master of the seesaw. That's because torque is equals to force into distance. And the greater the distance from the pivot or hinge, the greater the rotational effect. That's why doors open effortlessly when we push at the end rather than near the hinge. Torque or moment of force about a point depends on the following two factors: the magnitude of the force applied and the distance of line of action of the force from the axis of rotation. The chakki plays a crucial role in food industries, helping grind grains efficiently. But have you ever noticed how effortlessly the woman in the video rotates the upper stone? That's where physics plays a role. Here's the secret. The woman holds the handle at the farthest edge rather than near the center. Why? Because torque is equals to force into perpendicular distance, meaning the further the force is applied from the axis of rotation, the greater is effect. So before going further, we are going to understand few terms: types of physical quantities, mathematical derivation, and clockwise, anticlockwise motion. First, we will understand types of physical quantities. There are two types of physical quantities: vector and scalar quantities. Scalar quantities are those quantities which have only magnitude. Some example like speed, time, and distance. They only have magnitude. Scalar quantities always follow simple addition law. Now we will understand what is vector quantities. These quantities have both magnitude as well as directions. Now further, in brief, we will understand the two kind of product in vectors. Vectors have two kind of products: cross product and dot product. Cross product. The cross product of two vectors is always a vector. A cross B is equals to A B sine theta n cap. N cap denotes the direction. We can apply this formula as we see in the above example. Tau is equals to force cross R. Now we will understand what is dot product. the dot product of two vectors is always a scalar quantity. A dot B is equals to AB cos theta. We can apply this formula to find the work done. Work done is equals to F dot S. Time is something we all rely on. But have you ever paused to wonder why clock hands always move to the right? The reason lies in history, geography, and physics. Why do clock moves clockwise? Long before clocks were invented, people used sundials to tell time. In the northern hemisphere, the sun's shadow on a sundial moves in direction we now call clockwise, from left to right at the top, then downward on the right. So as far from here, we get to know about the two kinds of rotation, clockwise motion and anticlockwise motion. We mainly use these terms to describe the directions of rotation or the moment in a circular path. In physics, to differentiate the two motions, clockwise is assigned as negative sign and anticlockwise is assigned as positive sign. In the example given, to produce clockwise and anticlockwise motion, we need our two fingers which placed at 2 points geometrically opposite. This is due to produce couple effect, which help us to rotate the thing efficiently. A couple is a pair of equal parallel forces pointing in opposite directions in mechanics. The only thing a couple can do is cause or prevent a body from turning. The amount of either forces is multiplied by the perpendicular distance between their action lines to compute the turning effect or moment of a pair. The moment of a couple, also known as torque or rotational effect, couple consists of two equal and opposite forces acting parallel to each other. So have you ever been in a seesaw? When two people are sitting at the two opposite ends, for a period of time it moves clockwise and for the next period we can see anti-clockwise. We can clearly understand this interesting phenomena by the principle of moments. The principle of moments states that the total amount turning force about a pivot point is equal to the sum of the individual moments acting on that point. In simpler terms, if an object is balanced, the sum of clockwise moments is equals to the sum of the anti-clockwise moments about the pivot. Let's dive deeper into the phenomena described above. When two people of equal weight sit at opposite ends of a seesaw, we can observe that it does not move in either direction. This occurs due to equilibrium. Since the weights are equal, the forces they exert are also equal and opposite. As a result, they cancel each other out, and the seesaw remains in a state of rest. Now, let's explore the concept of equilibrium in more detail. A body is in equilibrium when the net external force and net torque acting on it are both zero. This means the body is not accelerating linearly or rotating, effectively staying in its current state of motion or rest. Equilibrium can be further classified as static, at rest, or dynamic, moving at constant velocity. Static equilibrium. In static equilibrium, the body is at rest and the sum of all forces and moments, torques, acting on it is zero. A book resting on a table is a good example of static equilibrium. In dynamic equilibrium, a body moves with a constant velocity, meaning it is neither accelerating nor deaccelerating. The sum of all forces and moments acting on the body is still zero. An airplane at the top, which is moving at a constant speed and height in a particular direction, is an example of dynamic equilibrium. Now let's take a look at a spinning top. When we rotate a top at a very high speed, it becomes perfectly balanced due to the dynamic equilibrium. The forces acting on it balance out the weight, allowing it to remain stable. That's all for today. In our next session, we will try to understand the concept of circular motion in detail.